Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I believe all of you are doing great, having a good time. So people, quickly let me know in the chats with some fire emojis if all of you can hear me, if I am perfectly audible and visible to every one of you. Quickly let me know in the chats with some fire emojis if all of you can hear me, if I'm perfectly audible and visible to every one of you. Yeah, is all clear? The audio, video, everything? Perfect, guys, perfect. So today we shall be starting the redox reaction chapter, and I'll try to cover this chapter completely in 2 to 3 sessions maximum, right? And the session duration is going to be 2.5 hours or 3 hours. Okay? Absolutely. Every single thing, whatever chapter I'll be doing here on this YouTube channel, right? All the chapters I shall be starting from the basics, from the scratch. I shall be assuming that you guys have not studied the chapter before. Okay? Every single thing shall be done from the basics, shall be started from the basics, from the scratch. You need not worry about anything. Okay? You need not to worry about anything. So are you all ready for the session? Are you all ready for the session? The ones who have not liked the session yet, I would want every one of you to smash the like and share this particular video with everyone. Whosoever cannot afford the paid batches, be it in offline or online, right? Share it with everyone so that every single student sitting anywhere in the country, right, gets benefited out of these sessions. Perfect? Perfect, people. So should we start? All ready? Are you all ready? And by the way, at the end of the session, I'll share the handwritten PDF in my Telegram channel, right? I hope you guys are already there in my Telegram. If not, then do join the Telegram channel, Wasim Bhatt Chemistry Official. That's the name of it. Okay? Right after the session, I'll be sharing the session PDF with all of you. Perfect? So without wasting a lot of your time, let's get going. Let's get started. Yeah? Let's get going. Let's get started with the chapter redox reactions. I think I need to turn some lights off. Yeah? Right? Let the dark mode begin. Let the dark mode begin. Yeah? Okay, just a second. Yeah, looks perfect now. Now it looks perfect. There are few students who are asking for the atomic structure part 2. I'll be sharing that with you in coming 2 to 3 days. Okay, I'll be sharing that with you in coming 2 to 3 days. Don't worry. Don't worry. Okay, so let's try to complete this chapter first. After that, we'll talk about the atomic structure, etc., etc. Perfect? Yes, the dark mode is on. Let's get going. Let's get started. So my dear students, this redox reaction chapter, let me tell you, this is one of the most important chapters of your chemistry. Let me honestly tell you, chapters like electrochemistry, okay, chapters like electrochemistry, which is there in your class 12, that is incomplete without this particular chapter. Okay, from this chapter in your NEET examination, like 2 questions for sure will be asked from this. Okay, so let's try to make this chapter as strong as possible. So the first topic with which I'll be starting this particular chapter, what is the name of that particular topic? My dear students, it's going to be oxidation state. Oxidation state. This is the first topic which we shall be doing over here, which forms the basis. It forms the basis of your chapter, redox reactions. oxidation state. So before letting you know exactly what oxidation state is all about, I'll write few lines about the term oxidation state, which I would want you guys to remember. Okay, have a look. If I talk about the term oxidation state, let me tell you, oxidation state, it is defined as the charge present on an atom, the charge present on an atom of an element, in a given compound. In a given compound. What exactly it means, you'll get the idea in some time, right? Before explaining all of this in detail, I'm going to write few lines over here. I'm going to write few statements over here. And after that, I'll make you understand what exactly it's all about. The charge present on an atom of an element in a given compound is what you call as oxidation state. Point number one. Point number two, the charge can be real or virtual. The charge can be real or virtual. Number three, in case of ionic compounds, the charge is real, and in case of covalent compounds, the charge is virtual. One last point, and after that, I'll be discussing all of this in detail. One last point. Oxidation state is defined for one atom of an element. Oxidation state is defined for one atom of an element. Now, my dear students, let's try to understand all of this. Let's try to understand all of this in detail from the scratch. Okay? Let's try to understand. Yes, you can consult this for JEE as well. Okay? You can consult this for JEE as well. Now, people, let's try to understand what this oxidation state exactly is all about. Look carefully what exactly I'll be talking about now. First of all, let me take an ionic compound. For example, I have got an ionic compound. Can you let me know in the chats what is the most common example of an ionic compound? You should be knowing this. Can you let me know in the chats what is the most common example of the ionic compound? You should know it. The most typical example of the ionic compound is basically your NaCl, sodium chloride, NaCl. This is the most typical example of your ionic compound. Now, my dear students, in case of NaCl, if I ask you how many elements do we have? In case of NaCl, we have got two elements, sodium and chlorine. These are the two elements which are present in NaCl, sodium and chlorine. Now, if I ask you, in NaCl, do you see any kind of charge present on sodium? You'll say no, there is no charge on sodium. If I ask you, do you see any charge present on chlorine? You'll say there is no charge mentioned on chlorine as well. Okay? But if you exactly have a look how this NaCl gets formed, you will exactly get an idea of what is exactly the charge present on one atom of sodium. You'll exactly get to know the charge present on one atom of chlorine. So right now, you must be thinking there is no charge on sodium, there is no charge on chlorine. But if you see exactly the formation of NaCl, if you exactly see how NaCl gets formed, then automatically you'll get to know the charge present on sodium as well as the charge present on chlorine. Now let's get to know exactly how this NaCl gets formed. Be careful and try to understand each and everything. My dear students, if I talk about sodium, what is the nature of sodium? Is it metallic or non-metallic? Sodium is metallic in nature. What about this chlorine? This chlorine, I must say, it is non-metallic in nature. Sodium, it is metallic in nature. Chlorine, it is non-metallic in nature. Now, As you all must be knowing, the metals, they have got strong tendency to lose electrons. If I talk about the non-metals, they have got strong tendency to gain electrons. So sodium being the metal has got strong tendency to lose electrons. Chlorine being the non-metal, it has got the strong tendency to gain electrons. Now, my dear students, if I particularly talk about the sodium, can you let me know sodium belongs to which group? Which group element sodium is? My dear students, let me tell you, sodium is the group first element. It belongs to alkali metals. It's a group first element. And let me tell you, all the group first elements, they have got one electron in their outermost shell. You should know it. All the group first elements, they have got one electron in their outermost shell. So this particular sodium, even this has got one electron in its outermost shell. Now you tell me, whether it is easy for sodium to gain 7 electrons or it is easy for sodium to lose 1 electron. I would say it is easy for sodium to lose 1 electron. So that is why the sodium, it loses 1 electron and gets converted into what? Gets converted into Na positive. So the sodium loses 1 electron and gets converted into Na positive. Now, if I talk about this chlorine, let me tell you, it's a group 17 element. It's a halogen. It's a group 17 element. And all the group 17 elements, they have got 7 electrons in their outermost shell. All the group 17 elements, they have got 7 electrons in their outermost shell. Now, what do you exactly think? Is it easy for chlorine to gain 1 electron or it is easy for chlorine to lose 7 electrons? What do you guys think? I would say it is definitely easy for chlorine to gain 1 electron. So what happens over here? The electron which was given by sodium, that electron will be accepted by this chlorine, and the chlorine, after accepting electron, gets converted into Cl negative. Okay? So sodium loses 1 electron completely and chlorine gains that 1 electron completely. What happens due to that? Due to that, cation gets formed as well as anion gets formed. Right, people? So over here, if you look carefully, 2 types of ions got formed. What all exactly? I would say Na positive as well as Cl negative. These 2 ions got formed. Okay. Now, my dear students, do you see you have got oppositely charged ions over here? Positive, negative. Absolutely, you have got oppositely charged ions over here. And between 2 oppositely charged ions, what kind of force of attraction will be there? Between 2 oppositely charged ions, I must say, there will be electrostatic force of attraction. There will be electrostatic force of attraction. And that electrostatic force of attraction, which holds these ions together, that electrostatic force of attraction, which holds these ions together, what do you call that as? You call that either as ionic bond, or you should be calling that as the electrovalent bond. Ionic bond or electrovalent bond. So that force of attraction, that electrostatic force of attraction which holds these ions together, right? That electrostatic force of attraction is something which you call as ionic bond, or you will be calling that as electrovalent bond. Now, my dear students, where exactly from where I started? I started from NaCl. I told you one question in the beginning. Do you see any charge on sodium? Do you see any charge on chlorine? I believe you all have the answer now. You will say the sodium in case of NaCl is basically present in the form of Na positive, and chlorine in case of NaCl is present in the form of Cl negative. So if I ask you, what is the charge present on 1 atom of sodium here? You will say the charge present on 1 atom of sodium is +1, and the charge present on 1 atom of chlorine is -1. And as per the definition, the charge present on 1 atom of an element, what do we call that as? The charge present on 1 atom of an element is something which we call as oxidation state. So I would say this +1 is nothing but it is the oxidation state of sodium in case of NaCl. This -1 is nothing but it is the oxidation state of chlorine in case of NaCl. I believe this is clear to everyone. Sir, please teach in Hindi. I think you should exactly see the name of the channel. It is Unacademy NEET English. Okay? Got it? Perfect, people. So, this +1, it is going to be the oxidation state of sodium in case of NaCl, and this -1 is going to be the oxidation state of chlorine in case of NaCl, right? So basically, if you ask me in depth, in detail, I would say the charge present on one atom of sodium is +1, which is what you call as oxidation state. The charge present on one atom of chlorine is -1, which is what you call as oxidation state. Okay? Now, my dear students, if I ask you one thing, since you saw exactly how this NaCl gets formed, you saw its formation, exactly. You saw its formation. Now, if I ask you one thing, if I talk about this sodium, it lost one electron completely. And chlorine gained that one electron completely. So can I say, during the formation of NaCl, can I say complete loss and gain of electrons has taken place? Yes, complete loss and gain of electrons has taken place. Sodium has lost one electron completely. Chlorine has gained that one electron completely. Right? And let me tell you, due to complete loss and gain of electrons, whatever charges arise on the atoms, these charges are going to be the real charges. These are the actual charges. These are the real charges. These are the actual charges. So real charges, or you can call them as the actual charges, they arise on the atoms due to what? Due to complete loss and gain of electrons. Okay? So I believe every single thing is clear till here. Right, people? I believe every single thing is clear till here. If yes, let me know once in the chats quickly. This was all about the ionic compounds. You exactly saw what is oxidation state of an element in case of ionic compound. Okay? Right? And I believe it's clear to everyone. Now people, try to understand very carefully. Now let's try to understand the same oxidation state concept in case of covalent compounds. In case of what? In case of covalent compounds. Since all of you must be familiar with the fact that in case of covalent compounds, which bond will be there? It's going to be a covalent bond. Just a second. I just need to turn the AC on because it's super hot here. Just a second, guys. Just give me a second, okay? Just give me a second. Just give me a second. All right. Where will you get the notes? You'll be getting the notes in my Telegram, which is Wasim Bhatt Chemistry Official. That is the name of the Telegram group. Now, guys, try to understand. Let me make you understand the term oxidation state in case of covalent compounds as well. Before talking about the term oxidation state in case of covalent compounds, if I ask you, which element in the periodic table is the most electronegative element? Your answer is going to be fluorine. Fluorine is the most electronegative element in the periodic table, followed by oxygen, followed by nitrogen, right? Followed by oxygen, followed by nitrogen. Fluorine is the most electronegative element in the periodic table, followed by what? Followed by oxygen, followed by nitrogen. If I ask you one more thing, on moving from left to right in the periodic table, what generally happens to electronegativity? You'll say, on moving from left to right in the periodic table, generally electronegativity increases. Similarly, on moving from top to the bottom in the periodic table, what happens to electronegativity generally? Electronegativity generally decreases. This is something which you all must be knowing. On moving from left to right, electronegativity increases generally. On moving from top to the bottom, electronegativity decreases generally. Right? Now, people, imagine that you have got a bond between A and B. Imagine that you have got a single bond between A and B. Okay? You have got a single bond between A and B. And I'm assuming this bond is covalent. It's a covalent bond. If it is a covalent bond, then what should happen? There should be, what is a covalent bond? In covalent bond, what happens? Mutual sharing of electrons. So, first of all, this single bond, in order to make this single bond, I would say one electron is given by A and one electron is given by B. In order to make this single bond, one electron has to be given by A, one electron has to be given by B. If this is supposed to be a covalent bond, then there should be mutual sharing of electrons. And if there should be the mutual sharing of electrons, I would say the electron pair exactly has to be at the center. The electron pair exactly has to be at the center. Now, my dear students, I'm assuming one thing. For example, if electron negativity of B is greater than that of electron negativity of A. If electron negativity of B is greater than that of electron negativity of A, what is going to happen? I would say if B is more electronegative than A, I would say B has got more tendency to attract the bonded pair towards itself. If B is more electronegative than A, that means B has got more tendency to attract the electron pair towards itself, due to which the electron density towards B, that's going to increase. And that increase in the electron density towards B, that is represented by delta negative. And that decrease in the electron density towards A, that's going to be represented by delta positive. Okay? Now, if I ask you, what do you think is the oxidation state of A over here? What do you think is the oxidation state of B over here? You will directly say the oxidation state of A over here is +1. The oxidation state of B over here is -1. Okay? But the point is, if I ask you whether this +1 is the real charge on A, whether this -1 is the real charge, actual charge on A, the answer is going to be a big no. Real charges arise on the atoms due to complete loss and gain of electrons. But over here, was there any complete loss and gain of electrons? No. What happened exactly? There was just the displacement of electron pair towards B. It was just the displacement of electron pair towards B, due to which electron density towards B increased. And that increase in the electron density towards B, I'm representing with delta negative. Okay? Perfect. So, should I be calling these charges as real charges or virtual charges? I'll be calling them as the virtual charges. These are not the real charges. So, in case of covalent compounds, the charges which arise on the atoms, they are all the virtual charges. They are not the real charges. Okay? They are not the real charges. For example, people, let's say there's a double bond between A and B. Let's say there's a double bond between A and B. Okay? And at the same time, I'm assuming B is more electronegative than that of A. If B is more electronegative than that of A, then what should happen? I'll say both the electron pairs, they'll be shifted towards B, due to which B is going to get -2 delta charge, A is going to get +2 delta charge. If I ask you what is the charge present on one atom of A, if I ask you what is the charge present on one atom of B, so technically I'm asking you the oxidation state of A and B. Technically, I'm asking you the oxidation state of A and B, right? Because what is the oxidation state? Charge present on one atom of an element, right? You'll directly say the oxidation state of A over here is +2 and the oxidation state of B over here is -2. Okay? Now, again, if I ask you one more question, are these the real charges? They are not the real charges. They are the virtual charges. Because the real charges arise on the atoms due to complete loss and gain of electrons. But over here, is there complete loss and gain of electrons? No. There is just the displacement of electron pairs towards B. Okay? I feel it's perfect. Now moving ahead. Let's say, for example, you have got a triple bond between A and B. Let's say there's a triple bond between A and B. So how many electron pairs are here in between? There are 3 electron pairs. Assume that B is more electronegative. So I would say all the 3 electron pairs would have got shifted towards B, due to which B gets -3 delta, A gets +3 delta. So if I ask you what is the oxidation state of A over here, you'll say +3. Oxidation state of B over here, you'll say -3. And at the same time, if I ask you whether these charges are the real charges, no. These charges are the virtual charges. Right? They are the virtual charges. I feel this is clear. Let me take certain examples. People. For example, imagine that you have got HCl. Okay, imagine that you have got HCl. Imagine that you have got water. Imagine that you have got NH3. These are some common compounds which I took. HCl, H2O, and NH3. My dear students, if I talk about this hydrogen and chlorine, what do you think? Which one is more electronegative? Hydrogen or chlorine? I would say chlorine is more electronegative. If chlorine is more electronegative, can I say the electron pair will be shifted towards chlorine, due to which chlorine gets delta negative and hydrogen gets delta positive? So if I ask you, what is the oxidation state of this hydrogen over here? You'll say +1. What is the oxidation state of this chlorine over here? You'll say -1. Now again, if I ask you whether these charges are the real charges, no, these charges are not the real charges, they are the virtual charges. Okay, perfect. At the same time, if you talk about water, I believe you all will be knowing the structure of water as well. This is your H2O. This is your H2O. Now, my dear students, look at this particular bond. This particular bond is between oxygen and hydrogen. Yeah? This particular bond is between oxygen and hydrogen. Now, which one is more electronegative? Oxygen. So, I would say this electron pair will be shifted towards oxygen, due to which oxygen gets delta negative, hydrogen gets delta positive. Now, at the same time, if you talk about this particular bond, it is again between oxygen and hydrogen. Oxygen is more electronegative, so this electron pair will be shifted towards oxygen, due to which it gets delta negative, this gets delta positive, right? Now, people, just tell me one thing. If I ask you what is the oxidation state of oxygen here, oxidation state of oxygen, you will directly say as -2. What is the oxidation state of this hydrogen? You'll say it's +1. What is the oxidation state of this particular hydrogen? You'll say +1. Okay, right? Now, on the top of the water, on the top of oxygen, I'll write -2. On the top of hydrogen, what should I write? Should I write +1 or +2? On the top of hydrogen, I should be writing +1. Okay? So these are the oxidation states of hydrogen and oxygen in case of water. Perfect? Oxidation state is defined for one atom of an element. So if I'm asking you what is the oxidation state of hydrogen in water, that means I'm technically asking you what is the charge present on one atom of hydrogen. That means technically I'm asking you what is the charge present on one atom of hydrogen in case of water. And charge present on one hydrogen atom in water is +1. Okay? Right, people? I hope I'm clear. If you talk about this NH3, I believe all of you would be knowing about the structure of NH3 as well. This is the structure of your NH3. Now, my dear students, look at this particular bond first. This particular bond is between nitrogen and hydrogen. Which one is more electronegative? Nitrogen or hydrogen? Nitrogen definitely is more electronegative. So I would say this electron pair will be shifted towards nitrogen, due to which this gets delta negative, this gets delta positive. What about this particular bond? Due to this bond, again delta negative, again delta positive. Due to this particular bond, again delta negative, again delta positive. So if I ask you, what is the oxidation state of nitrogen here? You'll directly say -3. What is the oxidation state of hydrogen here? Oxidation state of hydrogen here is +1. Right? The charge present on one atom of hydrogen is +1. Now, if I ask you whether these charges are the real charges or virtual charges, you'll directly say these charges are the virtual charges. They are not the real charges. I believe it's clear to everyone. So, my dear students, I hope you got to know the essence of oxidation state. You exactly got to know what oxidation state is all about. If yes, let me know once in the chats quickly. Say yes or no in the chats quickly if every single thing is clear. Quickly, people. All clear? All clear till here? I want everyone to quickly let me know in the chats. Everyone means everyone. Everyone means everyone. Is every single thing crystal clear? Perfect. Perfect, people. Now, let's move on to one more thing. Let me tell you, there are certain rules which you need to remember. to calculate oxidation state. So what are the rules to calculate oxidation state? Let's get to know. Rules to calculate the oxidation state. There are few rules. There are few rules which you need to remember to calculate the oxidation state of different species, different elements. Okay. Now, what exactly are those rules? Let's get to know them one by one. Let's get to know them one by one. My dear students, the first rule which you need to know, what is that? Let me write that. Oxidation state of an element. Oxidation state of an element in its standard state. Oxidation state of an element in its standard state or native state or the elemental state is taken as zero. Is taken as zero. Now, you must be thinking, what is meant by the standard state of an element? Let me first of all tell you, standard state, if I talk about the standard state of an element, standard state is basically the most stable state of an element. The most stable state of an element, or let me write it more precisely, most stable state of an element thermodynamically. That state of an element which is thermodynamically the most stable state of an element, that is something which you call as the standard state of an element. And whenever the element is present in its standard state, its oxidation state will be taken as zero. Now, my dear students, let's have a look upon certain things. If I ask you, in which state hydrogen exists in nature? In which state hydrogen exists in nature? In nature, hydrogen exists in the form of H2 gas. So this is something I'll be calling as the standard state of hydrogen. In which state chlorine exists in the nature? Chlorine in nature exists in the form of Cl2 gas. Chlorine in nature exists in the form of F2 gas. Bromine in nature exists in the form of Br2 liquid. Mercury in nature exists in the form of Hg liquid. Zinc in nature exists in the form of zinc solid. Iron in nature exists in the form of Fe solid. So these are all the standard states of these elements. This is the standard state of hydrogen. This is the standard state of Cl2, right? F fluorine, bromine, mercury, zinc, iron. And whenever you'll be having any element present in its standard state or native state or elemental state, its oxidation state is taken as zero, right? So oxidation state of hydrogen here is zero. This is zero, this is zero, this is zero. Everywhere the oxidation state is going to be zero. Perfect. Point number one. Point number two, here only in this particular rule. What is that? My dear students, remember, whenever you see an element having allotropes, let's say you've got an element which has got two allotropes, A1 and A2. Let's say you've got an element which has got two allotropes, A1 and A2, right? Now, which allotrope is considered as the standard state of this element? That allotrope among these two, which will be thermodynamically more stable. That allotrope among these two, which will be thermodynamically more stable, will be considered as the standard state of the element. For example, if this A2 is thermodynamically more stable, allotrope of this particular element, so this A2 I'll be calling as the standard state of the element. Therefore, A2 will be called as the standard state of the element. For example, if I, for example, talk about carbon. If I talk about carbon, what are the two main allotropes of carbon? If I ask you, you will say the two main allotropes of carbon are your diamond and graphite. Your diamond and graphite. These are the two main allotropes of carbon, right? In case of diamond, all of you must be familiar with the fact every carbon is attached with 4 other carbon atoms. In case of graphite, every carbon is attached with 3 other carbon atoms. If you look at the structure of diamond and graphite, let me tell you, in case of diamond, every carbon is attached with 4 other carbon atoms. In case of graphite, every carbon is attached with 3 other carbon atoms. Now, if I ask you, among these two, diamond and graphite, who do you think will be thermodynamically more stable? Since carbon has 4 electrons in its valence shell, since carbon has 4 electrons in its valence shell, over here, in case of diamond, carbon has utilized all these 4 electrons. But in case of graphite, no doubt, carbon has 4 valence electrons, but it has utilized only 3. So there'll be 1 electron as such on carbon in case of graphite. Now, if I ask you which one is thermodynamically more stable, which one is thermodynamically more stable? Which one is thermodynamically more stable? People are saying diamond is thermodynamically more stable, but it is not the diamond which is thermodynamically more stable. It is the graphite which is thermodynamically more stable. What is the logic? What is the reason behind that? Let me give you the most probable reason why graphite is thermodynamically more stable than diamond. Let's have a look. My dear students, I believe you guys would be knowing about the structure of graphite. I believe you guys would be knowing about the structure of graphite. If I talk about graphite, graphite has got a layered structure. Graphite has got a layered structure like this. I'm making one layer over here. This is, for example, one of the layer of what? Of graphite. This is one of the layer of graphite, for example. This, for example, one of the layer of graphite. Just down this layer, there'll be one more layer. Down that layer, there'll be one more layer. Right? Graphite has got the layered structure. This is one layer. Down it, there'll be one more layer. Down there, there'll be one more layer, etc., etc. There are a lot of layers in graphite. Now, my dear students, in case of graphite, as I told you, every carbon, see, this is your carbon. Every carbon is attached with 3 other carbon atoms. So there'll be an electron here. Since every carbon is attached with 3 other carbon atoms, so there'll be one electron on every carbon. There will be one electron on every carbon here. If there is one electron on every carbon here, can I say there is a probability for the formation of pi bond here? Yes. Probability of pi bond formation, probability of pi bond formation, probability of pi bond formation, probability of bond formation here, right? Similarly, among these two, probability of bond formation, pi bond formation, etc., etc., right? Now, my dear students, if there is a probability of bond formation, what do you observe over here? Can I say over here in this layer, you got alternate pi sigma conjugation, pi sigma everywhere, right? Alternate pi sigma conjugation. And wherever you see alternate pi sigma conjugation, can I say there is the possibility of resonance here in graphite? And any such molecule wherein there is the probability of resonance, that is definitely going to be more stable, right? So among diamond and graphite, which one is thermodynamically more stable? It is graphite which is thermodynamically more stable. So if I ask you what is the standard state of carbon, you're not going to say diamond is the standard state of carbon. You will say graphite is the standard state of the carbon. And whenever you see an element present in its standard state, its oxidation state will be taken as 0. This was your rule number 1. This was your rule number 1. I believe I'm clear. Now, talking about the rule number 2. Talking about the rule number 2. My dear students, the rule number 2 says that the oxidation state of group 1 and group 2 elements, is taken as +1 and +2 respectively. The oxidation state of group 1 and group 2 elements is taken as +1 and +2 respectively. Now, what are your group 1 elements? Your group 1 elements are lithium, sodium, potassium, rubidium, cesium. These are your group 1st elements, which are what you call as alkali metals. So these are your alkali metals. Now, your group 2nd elements. Group 2nd elements, they consist of beryllium, magnesium, calcium, strontium, and barium. And this group 2nd, is what you call as alkaline earth metals. This is what you call as alkaline earth metals. My dear students, let me tell you, oxidation state oxidation state of group first elements is taken as +1 and oxidation state of group second elements is taken as +2. Wherever from now onwards, in any compound, if you see group first element, take its oxidation state directly as +1. If you see group second element, take its oxidation state directly as +2. Okay? Whatever compound it's going to be. Group first elements, they are always going to show +1 oxidation state. Group 2 elements, they are always going to show the oxidation state of +2. Okay? This was your rule number 2. Now, talking about the third rule. The third rule which I'm going to give you right now, that is particularly dedicated to hydrogen atom. Okay? That's particularly dedicated to hydrogen atom. Now, my dear students, if I talk about hydrogen, the first thing about hydrogen, whenever you see hydrogen present in its standard state, that means in this form, H2 gas, this is the standard state of hydrogen. Whenever you see hydrogen present in its standard state, its oxidation state will be directly taken as 0. Point number 1 about hydrogen. Point number 2. Whenever you see hydrogen attached to more electronegative element than itself. Whenever you see hydrogen attached to more electronegative element than itself, the oxidation state of hydrogen will be taken as +1. For example, you can take a lot of examples here. Let's say you've got HCl. Let's say you've got H2O. Let's say you've got NH3. In all these three cases, if I ask you, is hydrogen attached to more electronegative element than itself? Yes. Is hydrogen attached to more electronegative element than itself? Yes. Is hydrogen attached to more electronegative element than itself? Yes. And whenever hydrogen is attached to more electronegative element than itself, the oxidation state of hydrogen is taken as +1. So, the oxidation state of hydrogen everywhere here is going to be +1. Moving ahead. My dear students, whenever you see hydrogen attached to the less electronegative element than itself, remember, oxidation state of hydrogen is taken as -1. Whenever you see hydrogen attached to less electronegative element than itself, okay, right? The oxidation state of hydrogen will be taken as -1. What are the examples here? You can take a lot of examples. Let's say you've got LiH, lithium hydride. Let's say you've got CaH2, calcium hydride. Let's say you've got MgH2. Okay. Now over here, if you observe carefully, hydrogen is attached to less electronegative element than itself. Hydrogen is attached to less electronegative element than itself. Hydrogen is attached to less electronegative element than itself. And whenever you see hydrogen attached to less electronegative element than itself, the oxidation state of hydrogen is taken as -1. So these are the three things which you need to remember about hydrogen particularly. Okay. Now, these were the three rules. Moving on to the fourth rule. Fourth rule is important, my dear students. And fourth rule is particularly for which element? It is particularly for oxygen. Fourth rule is particularly for oxygen. Now, understand and remember things. Okay. First thing, if I talk about oxygen, whenever you see oxygen present in its standard state, that means whenever you see oxygen in this form, O2 gas form, remember the oxidation state of oxygen will be taken as 0. Point number 1. Point number 2. My dear students, whenever you see oxygen attached to less electronegative element than itself, generally it's going to show the oxidation state of -2. Whenever you see oxygen attached to less electronegative element than itself, right? Whenever you see oxygen attached to less electronegative element than itself, generally the oxidation state of oxygen will be taken as -2. You can take a lot of examples here in the second case. For example, let's say you've got MgO. Let's say you've got H2O. Let's say you've got Cl2O. If you look at all these cases, oxygen is attached to less electronegative element than itself. Oxygen is attached to less electronegative element than itself. Oxygen here is attached to less electronegative element than itself. And whenever you see oxygen attached with less electronegative element than itself, the oxidation state of oxygen will be taken as -2. Okay. Now, the next rule related to oxygen. Oxygen forms certain special compounds. Oxygen forms certain special compounds, out of which the first one which I'm talking about, that's peroxide. Oxygen forms peroxides. Oxygen forms peroxide. Okay. What is peroxide? My dear students, whenever you see oxygen present in this form, O2 dinegative form, whenever you see oxygen present in O2 dinegative form, understand and remember, oxygen has formed a peroxide. And whenever oxygen forms the peroxide, oxidation state of oxygen will be generally taken as -1. For example, one of the most common example over here is your H2O2. Second example you can take, that is your Na2O2, right? If you look at the structure of H2O2, if you look at the structure of your hydrogen peroxide, look at it carefully. Look at it carefully. My dear students, this particular bond is between oxygen and hydrogen. This particular bond is between oxygen and hydrogen. Now, if I ask you, which one is more electronegative out of these two? You'll say oxygen is more electronegative. So this electron pair will be shifted towards oxygen, due to which this oxygen gets -1, hydrogen gets +1. What about this particular bond? Which one is more electronegative? Oxygen. So this electron pair gets shifted. So -1, +1. What about this particular bond? Nothing is going to happen due to this particular bond, because on one side there is oxygen, on one more side there is also oxygen. The tendency with which this oxygen is going to attract the electron pairs towards itself, with the same tendency, this particular oxygen is going to attract the electron pairs towards itself, due to which the electron pair is exactly going to be at the center. It is not going to shift. It's not going to shift. And let me tell you, whenever you see such kind of the linkage, such kind of the single bonded linkage between two oxygen atoms, oxygen single bond oxygen, this linkage is what you call as the peroxide linkage. This linkage is what you call as the peroxide linkage. Oxygen single bond oxygen is what you call as peroxide linkage. It's what you call as the peroxide linkage. Okay? And whenever oxygen forms the peroxide, its oxidation state is taken as -1. You can check it out. What is the charge present on one atom of oxygen? The charge present on one atom of oxygen here is -1. And the charge present on one atom of an element, what do you call that as? That's something which you call as oxidation state. Okay? Talking about this oxygen a bit more. My dear students, oxygen, it forms some more compounds as well. It forms some more compounds as well. Oxygen forms superoxides as well. It forms superoxides as well, right? So basically, whenever you see oxygen in this form, O2 negative form, whenever you see oxygen present in this form, O2 negative, understand? Oxygen has formed the superoxide. There are examples as well. Let's say you have got, for example, you have got RbO2, rubidium superoxide. Let's say you have got KO2, potassium superoxide, etc., etc. Right? These are the superoxides. Now, people try to understand carefully. Whenever you see oxygen present in this form, O2 negative, understand and remember oxygen has formed the superoxide. Now, when oxygen forms the superoxide, let me tell you, oxidation state of oxygen is taken as -1/2. You can check it out as well. See, on two oxygen atoms, the charge present is -1. If two oxygen atoms are having the charge -1, therefore, one oxygen atom will have the charge of -1/2. And the charge present on one oxygen atom is something which you call as oxidation state. So oxidation state of oxygen when it forms the superoxide, that's going to be -1. Okay. Now, the question is, can oxygen show positive oxidation states? The answer is a big yes. Oxygen can form positive oxidation states. In which case? In case of oxyfluorides. In case of oxyfluorides. And these oxyfluorides, they contain two compounds. One is your OF2 and one is your O2F2. Now look at their structures. If you talk about OF2, this is how your OF2 looks like. If you talk about O2F2, this is how your O2F2 looks like. Now people try to analyze carefully. Try to analyze carefully. Look at this particular bond. This particular bond is between oxygen and fluorine. Now, if I ask you which one is more electronegative, you will say fluorine is more electronegative. If fluorine is more electronegative, I would say this bond pair will be shifted towards fluorine, due to which -1 and +1. This bond pair also will be shifted towards fluorine. So -1, +1. So what is the charge present on one atom of oxygen? +1 +2 makes it +2. The oxidation state of oxygen in case of OF2, it is +2. If I ask you what is the oxidation state of oxygen here in O2F2, understand carefully. See, this particular bond between oxygen and fluorine, which one is more electronegative? Fluorine. So this bond pair is shifted towards fluorine. So -1, +1. This bond pair is shifted towards fluorine. -1, +1. Nothing is going to happen due to this bond pair. Because on one side you've got oxygen, on one more side, again you've got oxygen, right? So the tendency with which this oxygen is going to attract this electron pair towards itself, with the same tendency, this particular oxygen is going to attract this particular bond pair towards itself, due to which this electron pair is exactly going to remain at the center. So now, if I ask you, what is the oxidation state of oxygen here? That means I'm asking you, what is the charge present on one atom of oxygen? Check it out. The charge present on one atom of oxygen here is +1. Okay, so oxidation state of oxygen in case of O2F2 is definitely +1. Okay, now, does oxygen show some more oxidation states? Yes, oxygen forms ozonide as well. Oxygen forms ozonide as well. Whenever you see oxygen in this form, O3 negative, whenever you see oxygen in this format, O3 negative format, understand oxygen has formed the ozonide. For example, you have got KO3. You have got KO3. Okay, whenever you see oxygen in this form, O3 negative form, understand and remember oxygen has formed what? Ozonide. Now, people, what is the oxidation state of oxygen when it forms the ozonide? It's very simple, I would say. See, on 3 oxygen atoms, the charge present is -1. On 3 oxygen atoms, the charge present is -1. If the charge present on 3 atoms is -1, so what should be the charge present on 1 oxygen atom? 3 atoms carry the charge -1. So 1 atom will carry the charge of -1/3. And the charge present on 1 atom of an element is something which you call as oxidation state. So oxidation state of oxygen when it forms ozonide, it's going to be -1/3. So these were some important things when it comes to the element oxygen, which is very, very special for us. Yeah? All clear till here? All clear, people, till here? This was about what? This was about oxygen. Moving ahead. Moving ahead. How many rules are we done with? We are done with 4 rules. Now the 5th rule. The 5th rule is particularly designed for halogens. What are your halogens? Halogens are your group 17 elements, which are represented by X, chlorine, bromine, iodine, astatine. Right? These are your halogens. Halogens are generally represented by what? They are represented by X. Now, my dear students, what about halogens? What do halogens do? Understand. First point related to halogens. Whenever you see halogen present in its standard state, whenever you see a halogen present in its standard state, right, its oxidation state will be taken as 0. This is something which all of you must be knowing now. Okay? Point number 2. Point number 2. Whenever you see halogen attached to less electronegative element than itself, whenever you see halogen attached to less electronegative element than itself, let me tell you, the oxidation state of halogen will be taken as -1. You can take a lot of cases. I mean, you can take a lot of examples. For example, you have got HCl. Okay. Perfect. Let's say you have got NaCl. Right? Okay. If I talk about this chlorine and this chlorine, chlorine is a halogen. Chlorine is a halogen. Halogen is attached to less electronegative element than itself. Halogen is attached to less electronegative element than itself. And whenever you see halogen attached to less electronegative element than itself, oxidation state of halogen will be taken as -1. Okay. Now the point is, does halogen show positive oxidation state? Can halogen show positive oxidation state? The answer is yes. Halogen shows positive oxidation state. My dear students, whenever you see halogen attached to more electronegative element than itself, whenever you see halogen attached to more electronegative element than itself, the oxidation state of halogen can be positive. It can be positive as well. For example, Let's say I've got Cl2, here chlorine is the halogen, which I'm underlining. Let's say I've got IF7, the halogen which I'm underlining here, that's iodine. Okay. Let's say I've got BrF3, the halogen which I'm underlining, that's for example your bromine. Okay. Right, people? Now understand, if you talk about the Cl2, look at its structure. This is your Cl2. Look at this particular bond. This particular bond is between oxygen and chlorine. Which one is more electronegative? Oxygen. So this bond pair will be shifted towards oxygen. So -1 plus 1. Due to this particular bond, -1 plus 1. So charge present on one chlorine atom here is +1. So oxidation state of chlorine, oxidation state of halogen here is +1. Yeah? Right, people? Now, look at this IF7. Look at this iodine. Iodine is attached to 7 fluorine atoms. Iodine is attached with 7 fluorine atoms with the help of single bonds. So 7 single bonds. 7 single bonds. 7 single bonds. 7 single bonds. What do you think? What do you think? What will be the oxidation state of iodine here? Quick. What will be the oxidation state of iodine here? It has to be +7, right? Oxidation state of bromine here. It is attached to 3 fluorine atoms. So from one fluorine, this bromine gets +1. From other fluorine, bromine again gets +1. From other fluorine, bromine again gets +1. So +1 plus 1 plus 1 makes it +3, right? Perfect. So my point is, if question is asked like, can halogen show positive oxidation state? The answer is a big yes. The answer is a big yes, right? The answer is a big yes. And I believe I'm clear to everyone about this particular stuff. Quickly, let me know in the chats if all the things are clear. Quickly, let me know if all these things are clear. So this was all about the halogens. Now, guys, there is one more thing. There is one more thing. By the way, what do you call this particular compound as? Or what do you call this particular compound as? See, iodine is a halogen. Chlorine is also the halogen. So two different halogens have combined and formed a compound. Two different halogens have combined and formed a compound. So whenever two different halogens combine and form the compound, you call these particular compounds as the interhalogens. These are your interhalogens. So in case of interhalogens, the halogens are going to show the positive oxidation state. I hope this is clear. Now, my dear students, talking about the sixth rule, sixth point, that is related to coordinate bond. I believe all of you would be knowing about coordinate bond, which is called as dative bond as well, right? Which is called as dative bond as well. Okay? Which is called as dative bond as well. For example, if there is a coordinate bond between A and B, if there is a coordinate bond between A and B, and this particular A, I'm calling as the donor atom. This is your donor atom, and this is your acceptor atom. One is your donor atom, one is your acceptor atom. Donor, acceptor. There are few things which you need to remember over here. Point number one. If, for example, electronegativity of A, if electronegativity of A is less than that of electronegativity of B, if the electronegativity of donor is less than that of electronegativity of acceptor, at that point of time, the contribution of the coordinate bond towards A, you'll be taking +2, and here you'll be taking -2. Okay, when do you do this? If the donor atom is less electronegative, acceptor atom is more electronegative. At that time, donor gets a +2 due to the coordinate bond, and acceptor gets -2 due to the coordinate bond. Okay. Now, if, for example, the donor atom is more electronegative than the acceptor atom, if the donor atom is more electronegative than the acceptor atom, what do we take at that particular case? At that particular case, we do not take any contribution of the coordinate bond. It will be 0-0. It will be 0-0. So remember these two things as well. Donor, if it is less, so +2. If donor is more electronegative, nothing. Okay? Acceptor atom, if it is more electronegative, -2. Acceptor atom, if it is less electronegative, Nothing, zero. Okay? So, these things you need to remember about coordinate bond as well. So, this was our 6th point and 6th rule, I must say. Now, talking about the 7th one. Talking about the 7th one. 7th one is about the radicals. 7th one is about the radicals. What are radicals? So, let me first of all write a statement. Radicals are considered. Radicals are considered as a single unit. Radicals are considered as a single unit. And the charge present on the radical is taken as its oxidation state. Now, what is a radical? First of all, I'm not talking about the free radical here. Radical is nothing. Radical is defined as atom or group of atoms. Atom or group of atoms having any sort of charge on them. Atom or group of atoms having any sort of charge on them, you call them as a radical. For example, you have got Na positive. This is the atom carrying charge. It's a radical. You have got Cl negative. Atom carrying charge. It's a radical. You have got PO4 tri-negative. Group of atoms carrying charge. It's a radical. You have got SO4 di-negative. Group of atoms carrying the charge. It's a radical. You have got C2O4 di-negative. Group of atoms carrying the charge. It's a radical. You have got O di-negative. It's a radical. N tri-negative. It's a radical. So atoms or group of atoms having any sort of charge on them, you call them as the radicals. And my dear students, radicals, they are considered as a single unit, and whatever charge is present on them is taken as their oxidation state. So if I ask you, what is the oxidation state of sodium here? You'll say +1. Oxidation state of chlorine here, -1. Oxidation state of PO4 here, -3. Over here, -2. Over here, -2. Over here, -2. Over here, -3. So radicals are basically the atoms or group of atoms which have got any sort of charge on them, right? And people, remember, radicals are considered as a single units. Radicals are considered as a single unit, and the charge present on the radical, it will be taken as its oxidation state. Okay? Am I clear? Yes, CO3 di-negative as well. That's also the radical. Okay, for your wish, I'm writing CO3 di-negative as well. So it will be -2. Anything else? Any more examples you would want to give? You can give it, write it. Perfect. So this was about what? This was about the radicals. Now, my dear students, one more thing I would want to let you know over here. Do remember this. This is super important. This is super important. And this is for P block elements. This is for P block elements. This is for P block elements. My dear students, the P block elements, they show variable oxidation states. P block elements, they show variable, they show a range of oxidation states. P block elements, they show a range of oxidation states, right? They show a range of oxidation states. They do not show just one oxidation state. They show more than one oxidation states, right? Now you should remember one thing about P block elements. What is that range of oxidation states? How do we get to know the range of oxidation states which P block element shows? Remember, I'm writing it over here. Oxidation state of P block elements. It's always greater or equal to group number minus 10, group number minus 18 till group number minus 10. Till group number minus 10. This is something which I call as lowest possible oxidation state of your P block elements. Lowest possible oxidation states of your P block elements. This is something which I call as highest possible oxidation state of your P block elements. Let me give you the example as well so that you understand it properly. See guys, for example, I'm talking about the element oxygen. Let's say I'm talking about the element oxygen. If I ask you what is the group number of oxygen, you'll say the group number, it belongs to 16. Oxygen belongs to group 16, right? Oxygen belongs to group 16. Oxygen is a P block element. It belongs to group 16. Now, What are the range of oxidation states which oxygen shows? Understand. The range of oxidation states which oxygen shows. The oxidation state of oxygen will be greater or equal and less or equal to what? Group number minus 18. What is the group number 16? So 16 minus 18 comes out to be minus 2. Minus 2. 16 minus 10 comes out to be plus 6. So the lowest possible oxidation state which oxygen can show, that is minus 2. The highest possible oxidation state that oxygen can show, that's plus 6. That's plus 6. For example, talk about chlorine. This is also a p block element. What is the group number of chlorine? Group number of chlorine is 17. Group number of chlorine is 17. So talk about chlorine now. 17 minus 18 comes out to be minus 1. 17 minus 10 comes out to be plus 7. So if I ask you what is the lowest possible oxidation state, what is the lowest possible oxidation state in case of your chlorine? That's minus 1. What is the highest possible oxidation state of chlorine? That is plus 7. Okay, that's plus 7. That's plus 7. I believe I'm clear. I believe I'm clear. And after this, I would want you guys to remember two D block elements as well. I would want you guys to remember two D block elements as well, which I'll frequently using here. In case of D block elements. If you ask me, in case of D block elements, how can I find the highest possible oxidation state? It's going to be N minus 1 D electrons plus NS electrons. What do you mean by this? What do we mean by this? Try to understand. For example, I have got, let's say, chromium. What is the outermost configuration of chromium? You should know it. Outermost configuration of chromium is 3d5, 4s1. Okay. If this is N, that means this is N minus 1. So this is your NS. NS is carrying 1 electron. And this is your N minus 1. N minus 1D. It's carrying 5 electrons. So how many electrons are there in N minus 1D here? 5. In NS1. So 5 plus 1 comes out to be 6. 5 plus 1 comes out to be 6. So the maximum oxidation state that can be shown by chromium, that can be plus 6. That can be plus 6. Remember this. Okay. So first, I would want you guys to remember about chromium. Second, I would want you guys to remember about manganese as well. Okay. I'll be using it. What is the highest possible oxidation state of manganese? If you ask me. First of all, you should know the outermost configuration of manganese. It is 3d5, 4s2. 3d5, 4s2. So if this is your N, this becomes N minus 1. So this is your NS containing 2 electrons. And this is your N minus 1D containing 5 electrons. So 5 plus 2 comes out to be 7. So highest possible oxidation state that manganese can show, it is going to be plus 7. This is one more amazing thing which I would want you guys to remember. Okay? Do remember this, people. Do remember this. It's super important. Now, talking about a few more things about the oxidation state. How many rules are we done with? We are done with 8 rules. So let's have a look at the 9th one. The 9th rule that is super important. What is that? My dear students, do remember the sum of oxidation states of all the elements. The sum of oxidation states of all the elements in a molecule is equal to the net charge present on the molecule. The sum of oxidation states of all the atoms in the molecule, the sum of oxidation states of all the atoms in the molecule is equal to what? Is equal to the net charge present on the molecule. So if you'll be having a molecule, right? If there is a compound, for example, now in the compound, there will be a lot of elements. Okay. The sum of oxidation states of all the atoms present in the molecule, present in the compound, is always equal to the net charge present on it. Is always equal to the net charge present on it. For example, try to understand now. My dear students, I'm taking the example of MnO4 negative. Okay. Let's say I'm writing Cr2O7 di negative. Yes, you can do that. For example, we have got NH4 positive. We can write it. Okay. Let's say we have got simple carbon dioxide. Okay. Carbon dioxide. For example, I have got NO3 negative. NO3 negative. Okay. If I ask you to calculate the oxidation state of all these elements over here, calculate the oxidation states of all these elements over here, how do you do that? How do you do that? First of all, let me assume that oxidation state of manganese here is X. Okay. Oxygen generally shows -2. How many oxygen atoms? 4 atoms. Net charge -1. When you solve this equation, get the value of X. X value comes out to be +7. So +7 is the oxidation state of manganese in case of your MnO4 negative. Okay. Let the oxidation state of chromium be X. Oxidation state of chromium be X. Oxidation state means charge present on 1 chromium. If charge present on 1 chromium is X, therefore charge present on 2 chromium will be 2X. Plus, oxygen shows generally -2. How many oxygen atoms? 7 oxygen atoms. Net charge -2. When you solve this, the value of X comes out to be +6. Right? Look at this particular nitrogen. Let it be X. Hydrogen is attached to more electronegative element than itself. So hydrogen is going to show +1 oxidation state. How many hydrogen atoms? 4. Net charge is +1. When you solve this, X value will be -3. Right? Let the oxidations of carbon be X. Oxygen is going to show -2 oxygen state. There are 2 oxygen atoms. Net charge is 0. X value is +4. Let the oxidations of nitrogen be X. Oxygen is going to show -2. There are 3 oxygen atoms. Net charge is -1. X value is going to be +5. So this is how, my dear students, this is how you can calculate the oxidation states of different elements in case of different compounds. Isn't it simple? Let me take a few more examples so that it becomes properly clear to you. For example, I'm taking S4O6 dinegative. S4O6 dinegative. For example, I'm taking S2O3 dinegative. Let's say we have got Br3O8. Let's say we have got Fe3O4. Let's say we have got Fe2O3. For example, we have got NH4NO2. NH4NO2. For example, I've got few more. Let me take few more here. You have got, for example, C3O2. You have got C3O2. Let's say you have got FeCO5. FeCO5. For example, you have got K4. FeCN6. Now, the point is, how do we calculate the oxidation states of the underlying elements? See, guys, again, the same things. Whatever I've discussed with you till now, every single thing, I mean, should be clear to you, and with the help of it, you should be able to calculate the oxidation states of all these underlying elements. How exactly? Say, let the oxidation state of sulfur be X, so it becomes 4X. Oxygen shows -2. There are 6 oxygen atoms. Net charge is -2. When you calculate it, X value will be +2.5. X value will be +2.5. Okay. Let the oxidation state of sulfur be X, so it is 2X. Oxygen is going to show -2. There are 3 oxygen atoms. Net charge is -2 here. When you solve this, X value will come out to be how much? It will be +2, I believe. Right? Yes, +2. Now, this bromine. So it's going to be 3X. Oxygen is going to show -2. There are 8 oxygen atoms. Net charge is 0. So the value of X will come out to be +16/3. Okay. This iron over here, it's going to be 3X minus 4 2s are 8 is equal to 0. So X value is equal to +8/3. Okay. This iron, it's going to be 2X plus oxygen shows -2. -2 into 6 is, or let me write it, -2 into 3 is equal to 0. So X value is +3. X value is +3. Right? Right, people? Now, NH4NO2. Look at this particular compound. This NH4NO2 is a special one. It exists in the form of NH4 positive dot NO2 negative. It exists in the form of NH4 positive dot NO2 negative. Now here, I will be calculating the oxidation state of this nitrogen separately. I'll be calculating the oxidation state of this nitrogen separately. And in order to calculate the oxidation state of this nitrogen, what I'll be doing, I will be considering this particular part as the separate entity. And in order to calculate the oxidation state of this nitrogen, I'll be considering this particular part as a separate entity. Now, you can easily calculate it. Let the oxidation state of this nitrogen is X. Hydrogen is going to show +1. There are 4 hydrogen atoms. Net charge here is +1. When you solve this, the value of X is -3. Similarly, over here, when you solve this, the value of X is +3. So one nitrogen carries -3, second nitrogen carries +3. Okay? right? Now people try to understand. Try to understand here. C3O2. Let the oxidation state of carbon is X. So that makes it 3X plus oxygen will show -2. There are 2 oxygen atoms. Net charge is 0. The value of X comes out to be plus 4/3, right? This is carbonyl, CO, carbonyl. It's neutral. Remember this, it's neutral. Okay? If it is neutral, it does not carry any charge. Oxidation state is 0. Now, for iron, start with potassium. Potassium belongs to group first. Group first element shows +1. There are 4 potassiums. Plus, iron is going to show X. This is CN. CN is the ligand basically. Okay, I'm not using the term ligand. CN is basically, it is CN negative. It's a radical. CN negative. CN negative, it's a radical. Radicals are considered as a single unit. The charge present on them is termed as their oxidation state. So oxidation state of CN, here I'll be taking as -1. There are 6 CN. Net charge here is 0. When you solve this, you'll be getting the X value as +2 here. Right? Similarly, for example, you have got something like this. Fe 0.930. And I want you guys to calculate the oxidation state of iron. Let the oxidation state of iron here be X. Right? Let it be X. X multiplied by what? 0.93. So it's going to be 0.93X plus oxygen is going to show -2. The net charge is 0. Right? When you solve this, you'll be getting the value of X as 2 divided by 0.93, or you can write it directly as 200 divided by 93 with the sign plus over here. So this is the oxidation state of iron in case of this particular compound. Now, my dear students, as I told you in the beginning, oxidation state is basically the charge present on one atom of an element. Right? The charge present on one atom of an element. But you must be knowing about one more thing. Charge on an atom cannot be fractional. Right? Charge is always the integral value, right? Okay, it can be +1, +2, +3, -1, -2, -3. Have you ever seen on an atom charge is -2.005? No. Charge on an atom cannot be fractional. But over here, if you look carefully, the charge present on one sulfur atom came out to be +2.5. The charge present on one bromine atom came out to be +16/3. The charge on one iron atom came out to be +8/3. What does it mean? Does it mean charge present on one iron atom is +8/3? Does it mean charge present on one bromine atom is +16/3? No, that's not possible. That's not possible. Remember, people, whenever oxidation state of an element comes out to be fractional, remember, that is not the normal oxidation state of the element. That is the average oxidation state of the element. So, this +2.5, fraction, it is not the normal one. It is the average oxidation state. Okay? This one, +16/3, it is the average oxidation state. +8/3, it is the average oxidation state. Similarly, over here, +4/3, it is the average oxidation state. Now, what this average oxidation state is? Similarly, this one, it is the average oxidation state. Now, what is meant by the average oxidation state? You'll get to know that in some time. But before talking about the average oxidation state, there is one more super important statement which you need to know. What is that? I'm writing it over here. The maximum oxidation state of an element, the maximum oxidation state of an element can never be greater than. The maximum oxidation state of an element can never be greater than +7. The maximum oxidation state of an element, it can never be greater than +7, except osmium in osmium tetroxide, where the oxidation state of osmium is +8. This was the question once asked in AIMS as well. What is the oxidation state of osmium in OSO4? It is +8. It is +8. Okay? It is +8. Remember the oxidation state of an element. The oxidation state of an element, it can never be greater than +7. One exception you have to remember, which is in your syllabus. What is that? That is osmium. When it forms the osmium tetroxide, their oxygen shows +8 oxidation state. Rest, nowhere. Why this statement is very important? Why I told you this particular statement is very important? There is a logic, there is a reason behind that. For example, people, I'm giving you the compound CrO5. And I am asking you to calculate the oxidation state of chromium here. Will you be able to do it? Will you be able to calculate the oxidation state of chromium here with the help of formula which I gave you? You should be in a position to do that. You should be in a position to do that. You should be in a position to do that. See, I give you CrO5 and I'm asking you to calculate the oxidation state of chromium here. So you'll use the formula. Let the oxidation state of chromium is X. Oxygen shows -2. There are 5 oxygen atoms. Net charge is 0. The value of X comes out to be +10. But is the +10 oxidation state possible? Is the +10 oxidation state possible? The maximum oxidation state of an element can never be greater than +7. It can never be greater than +7. And over here it's coming out to be +10. What's the logic? What are we doing? What are we doing? This is not possible. This is not possible. That means there is some mistake which we are doing. There is some mistake which we are doing. We are assuming the oxidation state of all the 5 oxygen atoms as -2. This is something which we are assuming. We are assuming the oxidation state of all the oxygen atoms over here is -2. But what if some oxygen is present in the form of peroxide linkage? Right? How do we get to know that? We can only get to know that with the help of the structure. Okay? We'll get to know that with the help of what? With the help of structure. So there are certain structures which I would want you guys to remember. Because, for example, you got a compound like the CrO6. I'm asking you to calculate the oxidation state of chromium. What you'll do? You'll do X, and this is -2, this is 6, is equal to 0. So the value of X will come out to be 12, but 12 is not possible, right? So whenever oxidation state of an element with the help of formula comes out to be greater than +7, at that point of time, you need to consult the structure of that particular compound. So there are certain structures of certain compounds which you need to remember. I'm almost going to give you some 10 to 15 different structures of different compounds which are asked in the examinations. Nothing more than that is going to be asked. Okay, so mark the heading here as structures of some important compounds. Structures of some important compounds. Structures of some important compounds. The first compound, my dear students, which I'm taking, that is your same CrO5. CrO5. If you ask me how the CrO5 looks like, let me tell you the CrO5. The CrO5, we say it has got a butterfly-like structure. Though it is a myth, it is not completely true, I must say. Right? It's not actually butterfly-like. We say it has got a butterfly-like structure. Because when we make it on board, it looks like a butterfly. But in reality, it's not. Okay? CrO5. It has got a butterfly-like structure. And do remember one more thing about CrO5, which was long back asked in your JEE examination as well. What is the color of CrO5? Remember, it is deep blue in color. It is deep blue in color. Now, how the CrO5 looks like? It's simple. Cr double bond O. Oxygen, oxygen single bond. Oxygen, oxygen single bond. This is the structure of your CrO5. This is the structure of your CrO5. Now people try to analyze things. Look at this particular bond. It's a single bond between chromium and oxygen. Which one is more electronegative? Oxygen. So this electron pair will be shifted towards oxygen, right? So -1, +1. Due to this bond, -1, +1. Due to this bond, -1, +1. Due to this bond, -1, +1. Now here is a double bond. So both the electron pairs will be shifted towards this oxygen. So -2, +2, right? Now, if I ask you, what is the total charge present on chromium over here? +2, +3, +4, +5, +6. So actual oxidation state of chromium here is +6. Okay, actual oxidation state of chromium here is +6. If I ask you, what was the mistake exactly which we were doing? What we were doing? We were writing CrO5. This was X -2 into 5 is equal to 0. We were assuming that all the 5 oxygen atoms have got the oxidation state of -2. But look at the structure. Do all the 5 oxygen atoms are present in -2 oxygen state? No. Out of 5, only one oxygen atom is present in -2 oxidation state. All the 4 other oxygen atoms, they are present in -1 oxidation state. Okay, that was the mistake which we were doing, which we rectified with the help of the structure. Now guys, try to understand. Okay, will this bond make any difference? No, it's a peroxide linkage. On one side oxygen, on one side oxygen. Peroxide linkage, one side oxygen, one side oxygen. Nothing, right? Now, one more question that can be asked. How many peroxide linkage do you see in case of CrO5? This is one peroxide linkage, oxygen single bond oxygen, oxygen single bond oxygen. So there are 2 peroxide linkages. So how many peroxide linkages do we have? 2. If they ask you, how many oxygen atoms do we have which have got -1 oxidation state? How many oxygen atoms are there with -1 oxidation state? What you need to do? Calculate the peroxide linkage. Multiply the peroxide linkage with 2. Since there are 2 peroxide linkages, so 2 multiplied by 2 comes out to be 4. Simple. Simple, people. Nothing else. This was structure number 1. Structure number 2. Structure number 2. That is your CrO6, right? CrO6. This was asked, I believe, in NEET 2018, 19 or 20, one of the years. Okay. Now, people, CrO6, how it looks like, you should know it as well. This is chromium. This is oxygen, oxygen single bond. Over here, you have got oxygen, oxygen single bond. Right here, you have got oxygen, oxygen single bond. This is your CrO6. Now, tell me the oxidation state of chromium here. This is a single bond between chromium and oxygen. Which one is more likely to get oxygen? So this bond will be shifted towards oxygen. So oxygen gets -1, chromium gets +1. Due to this particular bond, -1 +1. Due to this particular bond, -1 +1. Due to this particular bond, -1 +1. Due to this bond, -1 and +1. Due to this bond, -1 and +1. So tell me the total charge present on this chromium here. +1, +2, +3, +4, +5, +6. So the actual oxidation state of chromium in case of CrO6, it is +6, right? Now, if I ask you how many peroxide linkage do you see? This is a peroxide linkage, oxygen single bond oxygen, oxygen single bond oxygen, oxygen single bond oxygen. So there are 3 peroxide linkages. How many oxygen atoms are there with -1 oxidation state? 2 multiplied by number of peroxide linkages. So 2 3s are 6. So there are 6 oxygen atoms with -1 oxidation state in CrO6. The third one. Third one is your Carose acid. What is the formula for Carose acid? It is H2SO5. H2SO5. You should know its structure as well. Well, H2SO5, it looks like this. S double bond O. This is double bond O. Oxygen attached with hydrogen. Oxygen, oxygen, and hydrogen. This is the structure of your H2SO5. Now, guys, try to understand. This is S double bond O. Which one is more electronegative? Oxygen. So both the bond pairs towards oxygen. So -2 +2. Due to this double bond, -2 and +2. Due to this single bond, -1 +1. Due to this single bond, -1 +1. Due to this single bond, -1 +1. Due to this single bond, nothing is going to happen. Due to this single bond, -1 +1. You calculated the oxidation status of all the atoms over here. So if I ask you what is the total charge on this sulfur here, check it out. +2, +4, +5, +6. So oxidation state of sulfur in case of Carose acid is +6. If I ask you, is there any peroxide linkage? Yes, I can find one peroxide linkage here. This is the peroxide linkage. How many oxygen atoms are there with -1 oxidation state? Check it out. This number of peroxide linkage multiplied by 2. Okay, this was one more structure. That's your Carose acid. Now, the fourth one. The fourth one, you must have heard about oleum, right? What is the structure of oleum? H2S2O7. How does it look like? How does this oleum looks like? How does this oleum looks like? Have a look. This is SOS, right? And here it's double bond O, oxygen attached with hydrogen, double bond O, oxygen attached with hydrogen. Okay, this is your H2S2O7. Now, my dear students, there is a double bond between sulfur and oxygen. Which one is more electronegative? Oxygen. So it will show -2. This will show +2. This double bond, -2 and +2. This single bond, -1 +1. This single bond, -1 +1, right? Now, if you look at the total charge on this sulfur will have +2, +3, +4, +5, +6. So +6 is the oxidation state of this sulfur. Similarly, this sulfur will also show +6 oxidation state. Now, how many sulfur atoms do you see here? You see 2 sulfur atoms. If there are 2 sulfur atoms, so let's calculate the average oxidation state of sulfur. Let's calculate the average oxidation state of sulfur. The first sulfur shows +6. The second sulfur shows +6. How many sulfur atoms are there? 2, right? So the average oxidation state of sulfur also comes up to be +6. Right? Now, over here there is no peroxide linkage, but there is one special linkage, that is SOS linkage. This can be asked. How many SOS linkages are there? There is one SOS linkage. In case of your oleum, H2S2O7. Got it? Got it, people, till here? So this was your fourth structure. Now, talking about the fifth one. Fifth one is something which you call as Marshall's acid. Marshall. What is the formula for Marshall's acid? H2S2O8. This is your Marshall's acid. And how does it look like? SOOS, double bond O, oxygen attached with hydrogen, double bond O, oxygen attached with hydrogen. When you calculate now, I'm not going to go into the details now. When you calculate the oxidation state of this sulfur, it will come out to be +6. When you calculate the oxidation state of this sulfur, it comes out to be +6. With the same procedure, whatever I have been showing you till now. Right? So, if I ask you the average oxidation state of sulfur here, the first sulfur is showing +6. Second sulfur is also showing +6. How many sulfur atoms? 2 sulfur atoms. So, average also comes out to be +6. Right? As simple as that. Now, after Marshall's acid, the sixth one, which I have. After Marshall's acid, it is your Na2S4O6. From this particular compound, 2 times question have been asked in JEE examination. Right? Na2S4O6. How does it look like? Remember its structure as well. This is S, 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 and S. This is double bond O, double bond O, double bond O, double bond O. Oxygen attached with sodium. Right? This oxygen attached with sodium. Na2S4O6. Now understand. Understand, people. This is something which I'll show you. This is S double bond O, correct? So due to this double bond, oxygen will show -2 and sulfur will show +2. Due to this double bond, again sulfur will show +2. Due to this single bond, sulfur shows +1. Due to this bond, nothing is going to happen. Due to this bond, nothing. This bond, nothing. This double bond, yes, +2 on sulfur. This double bond, +2 on sulfur. This single bond, +1 on sulfur. Now look at this particular sulfur. What is the total charge on this sulfur? +2, +4, +5. So +5 is the oxidation state of this sulfur. What is the oxidation state of this particular sulfur? +2, +4, +5. This is +5. The charge on this sulfur is 0. The charge on this sulfur is 0. If I ask you what is the average oxidation state of sulfur in case of Na2S4O6, you should be in a position to get that. The first sulfur is having +5. The second sulfur is having 0. Third is having 0. Fourth one +5. In total, there are 4 sulfur atoms. Right? When you solve this, the value comes out to be +2.5. So +2.5 is basically the average oxidation state of sulfur in case of your Na2S4O6. Yeah? Perfect. And once, as I told you, there was a question asked from this particular compound. The question was like this. The question was, correct. The correct set of oxidation state of sulfur in Na2S4O6. So what is going to be the correct set of oxidation state? It's going to be +5, 0, 0, +5. The correct set is going to be this one. +5, 0, 0, +5. Similarly, these 3-4 similar type of options were given, and this was the correct answer. Right, people? Am I clear till here? So this was your Na2S4O6, which was our sixth structure. Look at the seventh one. Seventh one is your K3CrO8. How it looks like? This is chromium. 2 oxygen atoms, single bond, oxygen, oxygen, oxygen. Right? And you got potassium atoms as well. Okay. Now, if I ask you directly, what do you think is the oxidation state of chromium here? See, chromium is forming 5 bonds with 5 oxygen atoms, right? 5 single bonds. So, if you look at this particular bond, oxygen will show -1, this will show +1. Similarly, -1, +1, -1, +1. So, in total, it's going to be +5 at the end, right? +5 at the end. If I ask you how many peroxide linkages do you see here? How many peroxide linkages? 1, 2, 3, and 4. There are 4 peroxide linkages. How many oxygen atoms are there with -1 oxidation state? 4 2s are 8. There are 8 oxygen atoms with -1 oxidation state. This was your K3CrO8. Now, the eighth one. The eighth one. This was your K3CrO8. Now comes your Br3O8. How it looks like? Br, single bond, Br, single bond, Br, double bond O, double bond O, here double bond O. Similarly, this is the structure of your Br3O8. Okay? If this is the structure of Br3O8, can you let me know the oxidation state of this bromine? Due to this double bond, it will be +2, +2, +2. Nothing will happen due to this. So it's going to be +6. +2, +2. So it's going to be plus 2 plus 2 plus 4 plus 2 plus 2 plus 2. So it will be plus 6. If you ask me what is the average oxidation state of bromine here, you can easily calculate. So first one having plus 6, second one plus 4, third one plus 6, 3 bromine atoms. So it's going to be plus 16 divided by 3. This is the average oxidation state of bromine in case of your Br308. I hope this is clear. Now, the ninth one. That is your C3O2. How the C3O2 exactly looks like. This is how your C3O2 looks like. People, if you ask me, carbon double bond O. So this has to be plus 2, this has to be minus 2. Due to this bond, nothing. Due to this bond, nothing. So this is 0. This is going to be plus 2. This will be minus 2. So average oxidation state of carbon here is going to be the first one plus 2, then 0, then plus 2. Divided by 3 carbon atoms. The value comes out to be plus 4 by 3. This is the average oxidation state of carbon in case of what? In case of C3O2. So how many structures do we have? 9 structures till now. Now, the 10th one. 10th one is your bleaching powder. 10th one is your bleaching powder. In case of bleaching powder, whose formula is COCaOCl2. In case of your bleaching powder, there are 2 types of linkages, right? One is your OCl linkage and one is chlorine directly attached with calcium, you can say. So let's say this is calcium and this, for example, OCl. Let's say one Cl is like this. Basically, it's an ionic compound, right? Just to get the oxidation states, I'm just making it like this. Now, look at this particular bond. It's between oxygen and chlorine. Which one is more electronegative? Oxygen. So minus 1 plus 1. This bond, minus 1 plus 1. This bond, minus 1 plus 1. What is the oxidation state of this calcium over here? It will be plus 2. What is the oxidation state of this chlorine over here? Minus 1. What is the oxidation state of this chlorine over here? Plus 1. What is the oxidation state of this oxygen here? Minus 2. Right? So one chlorine is carrying plus 1. One more chlorine is carrying minus 1. Average oxidation state of chlorine here will be. The first one is carrying plus 1. The second one is carrying minus 1. There are 2 chlorine atoms. Net charge is 0. Right? So average oxidation state of chlorine in case of bleaching powder, that is going to be 0. Right? Yes? Am I clear, people? Am I clear till here? This was your bleaching powder. Now, moving on to one more structure. So 10 structures done. 11th one. 11th one. BASCN whole twice. This is the compound which I'll use, right? Many a times in this chapter. That's why I'm giving you this compound. Similarly, you have got, for example, H3PO2. You have got H3PO3. You have got H3PO4. And at the end, you have got H3PO5 as well. Okay, look at their structures as well. BASCN whole twice. How does it look like? BASC triple bond N, SC triple bond N. H3PO2. Make it first of all P double bond O here. Make P double bond O here as well. Make P double bond O here as well. Make P double bond O here as well. Now, people, since there were 2 oxygen atoms, out of which one I have used, one I'm directly attaching with this, and hydrogen here. Similarly, 2 more hydrogen. H3PO2. This is how your H3PO3 looks like. This is how your H3PO4 looks like. This is how your H3PO5 looks like. Okay. Now, if you got their structures, if I ask you the oxidation states, now you can calculate the oxidation states easily now. See, this is a triple bond between carbon and nitrogen. Which one is more electronegative? Nitrogen. So all the 3 bond pairs towards nitrogen, due to which it will have minus 3, this will have plus 3. Now, this bond between sulfur and carbon. Which one is more electronegative? Sulfur. So minus 1 and plus 1. This bond, more electronegative sulfur, minus 1, plus 1. More electronegative is sulfur. So minus 1 and plus 1. More electronegative sulfur, minus 1, plus 1. More electronegative nitrogen, minus 3 and plus 3. Now calculate the oxidation state of each element over here. Nitrogen is present in minus 3 oxidation state. Carbon is present in plus 3 plus 1 plus 4 plus 3 plus 1 plus 4. Carbon is present in plus 4 oxidation state. Plus 4 oxidation state. Sulfur is present in minus 1 minus 2 oxidation state. Barium is present in plus 1, that is plus 2 oxidation state. Right? Okay. So this one is done. Now similarly, your H3PO2. If you talk about your H3PO2, this is the double bond between phosphorus and oxygen. Which one is more electronegative? Oxygen. So this is minus 2, this is plus 2. Right? Due to this single bond, minus 1, plus 1. Due to this single bond, minus 1, plus 1. Due to this single bond, phosphorus is more electronegative. So minus 1, plus 1. Minus 1, plus 1. So tell me the total charge on this phosphorus. Total charge plus 2, plus 3. Plus 3 minus 2 is plus 1. So plus 1 is the oxidation state of phosphorus in case of H3PO2. I hope this is clear. Similarly, when you calculate for this, it comes out to be plus 3. When you calculate for this, it comes out to be plus 5. When you calculate for this, it again comes out to be plus 5 only. So my dear students, these are some very, very, very important structures which I would want every one of you to remember from now onwards. Am I clear till here? Am I clear till here? Just tell me in the chats quickly. Everyone. Quickly, people. Done? All clear till here? Say yes or no. Say yes or no in the chats if every single thing is clear till here. These lectures are super enough for your NEET as well as JEE examination. Okay? Don't worry. Quickly, people. There will be no break. There will be no break. Why do you want to keep? Why do you want the break, by the way? So I believe the term oxidation state, rules to calculate oxidation state, and these structures, I believe these are perfectly clear to everyone. Yes? All right. Let's move on now to a term that is oxidation. Oxidation. So on one side, I'm writing oxidation. On another side, I'm writing reduction. One is your oxidation, one is your reduction. Try to understand, people, what exactly I'm going to say. What is oxidation exactly and what is reduction? Okay. So first of all, how do you exactly define the term oxidation? There are many ways by means of which you can define oxidation. Number one. Oxidation is defined as the loss of electrons. Let me give you an example as well. Let's say you've got magnesium. Let's say this magnesium, it is losing 2 electrons and getting converted into Mg di positive. So in this reaction, magnesium is losing 2 electrons, getting converted into Mg di positive. So this reaction is example of oxidation reaction. This reaction is the example of the oxidation reaction. Number one. Number two. Number two is your addition of oxygen. Number two is your addition of oxygen. Addition of oxygen is also called as oxidation, right? For example, you have got calcium plus half of O2. It gives what? It gives calcium oxide. In this particular reaction also, I would say addition of oxygen is happening. And addition of oxygen is also called as oxidation. Now, the third definition, that is the removal of hydrogen. Removal of hydrogen. Now, my dear students, let's say you have got a reaction like this, 2 times H2O. Let's say I'm taking hydrogen out of it. So 2 times H2 plus O2. In this particular reaction, what is happening? Hydrogen is being removed. Removal of hydrogen is also called as oxidation. Last one. Last one will be addition of more electronegative element. Addition of more electronegative element. Right? You can take the reaction as carbon plus 2 times Cl2 gives CCl4. In this reaction, more electronegative element is being added. Right? So these are basically different ways by means of which you can define the oxidation term. Similarly, reduction. Reduction will be opposite of it. Loss of electrons, so it's going to be gain of electrons. It's going to be gain of electrons. Addition of oxygen, so it's going to be removal of oxygen. It's going to be removal of oxygen. Similarly, removal of hydrogen, it's going to be addition of hydrogen. Addition of hydrogen. Similarly, addition of more electronegative element, it's going to be removal of more electronegative. Right? All these ways I can define the term oxidation and reduction. Now, the main and the important point. What is the main and the important point? Try to understand. All these are the reactions, all these are the examples of the oxidation reactions, right? Now, people, since all these are the examples of the oxidation reactions, now you'll find one thing common in them. You'll find one thing common in them. What is that? See, if I ask you what is the oxidation state of magnesium here, there is no charge, 0. The charge here is +2. So magnesium is changing its oxidation state from 0 to +2. 0 to +2. I would say increase in the oxidation state of magnesium is happening. Right? Similarly, this is 0 here and this will be +2 here. 0 to +2. Again increase in the oxidation state of an element. Right? See, this is -2 and this is 0. -2 to 0. Again increase in the oxidation state of an element. This is 0 here. This is +4. 0 to +4. Again increase in the oxidation state of an element. My dear students, if I ask you one thing, just try to understand. All these reactions are basically the examples of the oxidation reactions. Right? All these are basically the examples of the oxidation reactions. Now, did you find one thing common in all the oxidation reactions? Did you understand? Oxidation state of an element is increasing when the substance is undergoing oxidation. So do remember from now onwards, oxidation is nothing. It is just defined as the increase in the oxidation state. Increase in the oxidation state is something which we call as oxidation. Sir, do you know Shimon, sir? Shimon is a very close friend of mine. We have started our teaching career together. Shimon Joseph, yes. A very, very, very close friend of mine. I mean, we have taught together for 4 years. Do ask him. Yeah, he's a very close friend of mine. Okay, we have started our teaching career in Chennai. Him and me. Okay, so people, oxidation from now onwards, how you are going to remember it? Oxidation is nothing but increase in the oxidation state. Whenever you see an element undergoing increase in the oxidation state, increase in the oxidation state of an element is something which you call as oxidation. Similarly, how do you define the reduction? Decrease in the oxidation state of an element is something which you call as reduction. I believe these two things are clear, right? Oxidation and reduction. Increase in the oxidation state is what we call as oxidation, and decrease in the oxidation state is what we call as the reduction. Am I clear, people? Am I clear? Am I clear? Say it quickly in the chats. Now there are two more things. There is something called as oxidizing agent. There is something called as oxidizing agent. Oxidizing agent and the reducing agent. And the reducing agent. Oxidizing agent and the reducing agent. Let me first of all tell you, oxidizing agent is what you call as oxidant as well. Reducing agent is what you call as a reductant as well. Okay. Now, first of all, how do we define the two? Oxidizing agent or oxidant, it is defined as the substance that oxidizes others. The substance that oxidizes others, but itself undergoes a reduction. The substance that oxidizes others, but itself undergoes reduction. Similarly, reducing agent is the one that reduces others, but itself undergoes oxidation. So, my dear students, remember these two things first of all. Oxidizing agent is the one that oxidizes others, but itself will undergo reduction. Reducing agent is the one that reduces others, but itself will undergo oxidation. Once more, oxidizing agent is the one that oxidizes others and itself undergoes reduction. Reducing agent is the one that reduces others, itself undergoes oxidation. Now try to understand. Now try to understand. How do you exactly identify whether in a reaction a substance is behaving like the oxidizing agent or the reducing agent? Let's try to understand. See guys, for example, I'm writing one common reaction. The reaction is like this. Zinc plus copper dye positive gives copper plus zinc dye positive. This is the reaction, for example. I need to check which one is my oxidizing agent here and which one is my reducing agent here. See guys, if I ask you what is the charge on this zinc, it's 0. The charge on this copper here, it's +2. The charge on this copper here, it is 0. The charge on this zinc here, it's +2. So now understand, can I say the oxidation state of zinc is going from 0 to +2? 0 to +2 means increase in the oxidation state. Now talk about the copper. +2 to 0. +2 to 0 means decrease in the oxidation state. +2 to 0 means decrease in the oxidation state. Now, see, 0 to +2 means increase in the oxidation state. Let me tell you, increase in the oxidation state is something which you call as oxidation. Increase in the oxidation state is something which you call as oxidation. So I would say this zinc is undergoing oxidation. The one that undergoes oxidation, that undergoes loss of electrons. So zinc will be losing electrons. And if zinc is undergoing oxidation, the one that undergoes oxidation, you call that as the reducing agent. So this zinc is my reducing agent here. Similarly, if you talk about this copper dye positive, its oxidation state is decreasing from +2 to 0. Decrease in the oxidation state is something which we call as a reduction. And since copper dye positive, it's undergoing a reduction, so it will be gaining electrons. And the one that undergoes a reduction, that is something which I call as oxidizing agent. Right? Right, people? So this is how you get to know which is your oxidizing agent and which is your reducing agent. Okay? For example, let me take a few more. Let's say you have got a reaction like this. H2, a random reaction I'm taking. H2 plus 2 times Ag positive, it gives 2 times H positive plus 2 times Ag. This is the reaction, for example. Now, my dear students, try to understand. What is the oxidation state? What is the charge on this hydrogen here? 0. Charge on silver here, +1. Charge on hydrogen here, +1. Charge on silver here, 0. Right? Now, 0 to +1. Hydrogen, 0 to +1, increase in the oxidation state. Increase in the oxidation state is something which we call as oxidation. So this H2 is undergoing oxidation. If H2 is undergoing oxidation, it will be losing electrons. The one that undergoes oxidation, that's what we call as a reducing agent. So H2 is behaving like the reducing agent. Similarly, people, +1 to 0. +1 to 0 means decrease in the oxidation state. Right? +1 to 0, decrease in the oxidation state. So this Ag positive, since it's undergoing decrease in oxidation state, so I would say it's undergoing reduction. The one that undergoes reduction, that undergoes gain of electrons. The one that undergoes reduction, that's what we call as oxidizing agent. I hope it's clear. Right? Right, people? Similarly, let me take a few more examples where you can check whether the substance is oxidizing or reducing agent. For example, you have got a reaction like this. MnO4 negative plus Fe dye positive. Let's say it gives Mn dye positive plus Fe tri positive. If I ask you which one is my oxidizing agent here and which one is my reducing agent here, you should be able to answer this. See guys, calculate the oxidation state of manganese here. It will come out to be +7. Iron here, it will come out to be +2. This manganese +2. This iron +3. Now what is happening? Manganese is undergoing change in the oxidation state from +7 to +2. +7 to +2. Decrease in the oxidation state. Decrease in the oxidation state is something which you call as a reduction. So this MnO4 negative is undergoing a reduction over here. The one that undergoes reduction, that's my oxidizing agent. +2 to +3, increase in the oxidation state. Increase in the oxidation state is something which we call as oxidation. So this Fe dye positive is undergoing oxidation. The one that undergoes oxidation, that will be your reducing agent. So this is your reducing agent. For example, you have got the reaction like this. Cr2O7 dinegative plus C2O4 dinegative, right? Let's say it gives chromium tripositive plus carbon dioxide. This is your reaction, okay? This is your reaction. Now, first thing, oxidation state of chromium here. When you calculate it, it comes out to be +6. Carbon, when you calculate it, it comes out to be +3. This is +3. And this will be +4 when you calculate. Now, what is happening to the oxidation state of chromium? +6 to +3. +6 to +3. Decrease. Decrease means reduction. So this particular species overall is undergoing reduction. And the one that undergoes reduction, that will be my oxidizing agent. Similarly, +3 to +4, increase in the oxidation state. Increase in the oxidation state means oxidation. So this oxalate ion is undergoing oxidation. And the one that undergoes oxidation, that has to be my reducing agent. That has to be my reducing agent. Sir, reaction galat likhi hai. Where is the reaction galat? MnO4 negative plus Fe positive, Mn dipositive, Fe tripositive. This is right. Cr2O7 dinegative plus oxalate gives chromium tripositive plus carbon dioxide. No, this is right. Okay, both the reactions are right. Both the reactions are right. Perfect, people. Now, let's try to solve certain questions. Let me see whether you'll be able to answer them or not. See, guys. Just a second. Okay. These are the two questions which we have. These are the two questions which we have. The compound that cannot act both as oxidizing as well as the reducing agent. Which of the following among these four will not act both as oxidizing as well as the reducing agent? Now, people, how do we check that? How do we check that? Understand. First of all, let me mark the central atom over here. Okay, so this is phosphorus, nitrogen, sulfur, and oxygen. Do you see one thing common in all these elements? These are all the p block elements. Okay, these are all the p block elements. These are all the p block elements, right? Now, if they are the p block elements, what is the lowest possible and what is the highest possible oxidation state which p block elements show? Group number -18 to group number -10. Okay, this is the lowest possible oxidation state. This is the highest possible oxidation state. This is the highest possible oxidation state. Now try to understand. Over here you got phosphorus. If you talk about phosphorus, what is the group number of phosphorus? Phosphorus belongs to nitrogen family. So group number is 15. So oxidation state of phosphorus will range from 15 minus 18 is -3. 15 minus 10 is +5. So lowest possible oxidation state of phosphorus is -3 and it's +5. Okay. Talk about this nitrogen. Nitrogen. Its group number is also 15, right? Its group number is also 15. So it's valid for this as well. Now, talk about sulfur and oxygen. If I talk about sulfur and oxygen, what are their group numbers? Group number for sulfur and oxygen is 16. So their oxidation state will range from 16 minus 18 is -2. 16 minus 10 is +6. Okay. Right? Now we will try to understand very carefully. If I ask you what is the oxidation state of phosphorus here, you can calculate it. Oxidation state of phosphorus here is +5. Oxidation state of nitrogen, when you calculate it, +1 plus x minus 4 is equal to 0, so it will be +3. When you calculate this, +2 plus x minus 6 is equal to 0, so it will be +4, right? And this oxygen, hydrogen peroxide, -1. My dear students, look at this phosphorus. Phosphorus over here is in +5 oxidation state. Phosphorus over here is in +5 oxidation state. If you talk about phosphorus, what is the maximum oxidation state that phosphorus can show? Phosphorus can show maximum of +5 oxidation state. And phosphorus is already present in its maximum oxidation state. Right? Phosphorus is already present in its maximum oxidation state. If phosphorus is present in its maximum oxidation state, can it further increase its oxidation state? No. If it cannot further increase its oxidation state, it cannot undergo oxidation. If it cannot undergo oxidation, it cannot behave like the reducing agent. So this cannot behave like the reducing agent. If it cannot behave like the reducing agent, that means it will behave like the oxidizing agent. Got it? The question was, which of the following cannot act both as oxidizing and reducing agent? This cannot act both as oxidizing and reducing agent. If you look at the other ones too, check. Nitrogen is in +3 oxidation state. Nitrogen here is in +3 oxidation state. What is the lowest possible oxidation state that nitrogen can show? -3. Highest +5. Highest +5. Nitrogen can show the lowest of -3, highest of +5. And over here, nitrogen is present in +3. Nitrogen is present in +3. If nitrogen is present in +3, it can decrease its oxidation state as well as it can increase its oxidation state. If it decreases its oxidation state, it will undergo reduction. It will be behaving like the oxidizing agent. If it increases its oxidation state, it will undergo oxidation. It will behave as a reducing agent. So here, this acts both as oxidizing as well as reducing. Right? Right, people? Now, look at this sulfur. Sulfur is in +4 oxidation state. The minimum oxidation state that sulfur can show is -2, maximum is +6. And over here, sulfur is showing +4. Sulfur is showing +4. If sulfur is showing +4, it can decrease its oxidation state as well as increase its oxidation state. And when it decreases the oxidation state, it will undergo reduction. It will behave like the oxidizing agent. When it increases the oxidation state, it will undergo oxidation. It will behave like the reducing agent. So this one, it is also behaving like oxidizing as well as reducing. Even this one will be behaving both as oxidizing as well as a reducing agent. I hope I'm clear. Right? Now, look at this question. Identify the nature of the following. You need to identify the nature of the following, people. Nature means you have to check whether this is oxidizing agent or reducing agent. Oxidizing or reducing, oxidizing or reducing. You can check it. See, chlorine, manganese, nitrogen, chromium. Check the oxidation state of chlorine here. You can calculate it. It will come out to be +7. This will come out to be +6. This will come out to be +3. This will come out to be +6. Check it out. Chlorine. Chlorine is your group 17 element. Chlorine is your group 17 element. Group number for chlorine is 17. The minimum possible oxidation state that chlorine can show. 17 minus 18 is -1. -1 to 17 minus 10 is +7. This is the range of oxidation states that chlorine can show. This is the range of oxidation state that chlorine can show. Now understand. What is the oxidation state of chlorine here? It's +7. Oxidation state of chlorine is +7. But +7 is already the maximum oxidation state of chlorine. So I would say chlorine here is already present in its maximum oxidation state. It cannot further increase its oxidation state. It cannot further increase its oxidation state because it is already present in maximum oxidation state. It cannot further increase its oxidation. If it cannot further increase its oxidation state, it cannot undergo oxidation. If it cannot undergo oxidation, it cannot behave like the reducing agent. So it cannot behave like the reducing agent. That means it will behave like the oxidizing agent. Manganese. Manganese, D block element. I told you long back, what is the maximum possible oxidation state of manganese? +7. +7, right? +7. So manganese can go from +7, +6 to +7. It can decrease also. +6 to +2. You have seen manganese in +2 also, right? Mn di positive. So it can increase as well as decrease. If it can increase as well as decrease, it can show both oxidizing agent. It can behave like the reducing agent as well. Nitrogen here is in +3 oxidation state. Nitrogen here is in +3 oxidation state. So it can decrease as well as increase. So both oxidizing as well as a reducing agent. Okay. K2Cr2, so chromium. Chromium is in +6 oxidation state. And I told you long back, maximum possible oxidation state of chromium is +6. If maximum possible oxidation state of chromium is +6 and chromium is already in its maximum, so it cannot further increase because it's already in maximum. It cannot further increase its oxidation state. If it cannot further increase its oxidation state, that means it cannot undergo oxidation. It cannot behave like the reducing agent. So this one cannot behave like the reducing agent. That means it is going to behave like the oxidizing agent. I believe all of these questions you will be able to do on your own. Okay. For example, these two questions we have. This question will be your homework question. This question is your homework question. You should be in a position to answer this question on your own. Which of the following can work both as oxidizing as well as a reducing agent? Okay, which of the following can act both oxidizing as well as a reducing agent? Right? I have been telling you from so long how do we identify that. Now, which of the following cannot undergo disproportionation? What is disproportionation, first of all? For example, you have got A2. Let's say you have got A2, it's getting converted into A positive plus A negative. Let's say A2 gets converted into A positive plus A negative. Oxidation state of A here is 0, here it's plus 1, here it's minus 1. 0 to plus 1 means increase. 0 to minus 1 means decrease, right? So can I say oxidation state of same element is increasing as well as decreasing? Right? Oxidation state of same element is increasing as well as decreasing. Perfect. Whenever you see this kind of the scenario where oxidation state of same element increases as well as decreases, we say that species undergoes disproportionation. So A2 here is undergoing disproportionation. Its oxidation state simultaneously is increasing as well as decreasing. So A2 is undergoing disproportionation. Now we have to see which of the following cannot undergo disproportionation. My dear students, look at the last case. Look at the last case. If you calculate the oxidation state of chlorine here, it will come out to be plus 7. Is plus 7 the maximum oxidation state? Is plus 7 the maximum oxidation state of chlorine? Yes, plus 7 is the maximum oxidation state of chlorine. So over here in this question, I would say chlorine is already present in its maximum oxidation state. If chlorine is already present in its maximum oxidation state, can it further increase it? No. If it cannot increase it, can it undergo disproportion? No, it cannot undergo disproportion. Okay? For disproportion, element has to increase as well as decrease its oxidation state simultaneously. Okay? Right? Right, people? If you talk about this ClO, talk about chlorine, its oxidation state is plus 1 here, right? Its oxidation state is plus 1 here. Now, oxidation state of chlorine is plus 1. So it can decrease as well as increase. It can decrease as well as increase. So it can undergo disproportionation, right? It can undergo disproportion. Even this can undergo disproportionation. Even this can undergo disproportionation. This cannot undergo disproportionation. I hope this particular question is clear to all of you. Yeah? Am I clear? Am I clear, people? Now, there is one last question which can be asked when it comes to oxidation reduction. See, guys, sometimes they'll ask you the question related to the strength of oxidizing agent. They'll ask you which oxidizing agent has got more strength. Which is the better oxidizing agent? Which oxidizing agent has got more strength? What we need to do is remember, strength of oxidizing agent is directly proportional to the oxidation state of central atom. It is directly proportional to oxidation state of central atom. So more the oxidation state of the central atom, better is going to be the oxidizing agent. Similarly, they might ask you a question related to strength of reducing agent. Strength of reducing agent. Strength of reducing agent will be inversely proportional to oxidation state of central atom. They might ask you a question related to acidic strength. They'll give you certain acids. They'll ask you which of the following is strong acid. It is directly proportional to what? Oxidation state of the central atom. Remember these three things. You're sorted. Remember these three things. You're sorted. First one. They'll give you a lot of oxidizing agents. They'll ask you which one is better oxidizing agent. Which oxidizing agent has got more strength? Similarly, strength of reducing agent. Acidic strength. For example, these are few questions. These are few questions which we have, right? You need to arrange them on the basis of the strength of oxidizing agent. So basically, you have to check which of the following is the better oxidizing agent. What you'll be doing? You'll be calculating the oxidation state of the central atom. Calculate the oxidation state of nitrogen here. It will be -2. Nitrogen here, 0. Nitrogen here, +1. And you know how to calculate it. You know how to calculate it. I've given you the rules. Nitrogen, +2. Nitrogen, +3. Nitrogen, +4. Nitrogen, +5. So check. Where is the oxidation state of the central atom the maximum? Where is the oxidation state of the central atom the maximum? It's here. More the oxidation state of the central atom, stronger is going to be the oxidizing agent. I told you strength of oxidizing agent is directly proportional to Strength of oxidizing agent is directly proportional to oxidation state of the central atom. More the oxidation state of the central atom, better is the oxidizing agent. More stronger is the oxidizing agent. So this has to be the order. This is the order of the strength of oxidizing agent. Check here. What is the order of strength of oxidizing agent? If you talk about the oxidation state of this manganese +7, this manganese is +6, this manganese is +4, this manganese +3, this manganese +2. More the oxidation state of the central atom, stronger the oxidizing agent, more the strength of the oxidizing agent, right? Because they are directly proportional. Because strength of oxidizing agent is directly proportional to oxidation state of the central atom. Look here, nitrogen, here will be in +5 oxidation state, right? Chromium here will be in +6 oxidation state. Manganese here will be in +7 oxidation state. More the oxidation state of the central atom, more the oxidation state of the central atom, more the oxidation state of the central atom, stronger is the oxidizing agent, right? Because they are directly proportional. More the oxidation state of the central atom, stronger is the oxidizing agent. So what is the answer of this question then? Right? Achha, if this is the order of the oxidizing agent capability, what will be the order of the reducing agent? You can reverse this order. For the strength of a reducing agent, you can reverse it. You can reverse it. You can reverse it. Okay, you can reverse it. Now, the next question. Calculate the oxidation state +7. Here it is +5. Here, when you calculate it, it will be +3. Here, when you calculate it, it will be +1. Arrange the following on the basis of their acidic strength. Arrange the following on the basis of your acidic strength. I give you one order. Acidic strength is directly proportional to oxidation state of central atom here in this case. So, more the oxidation state of the central atom. More the oxidation state of the central atom. More the oxidation state of the central atom, more is going to be the acidic strength. So this is the acidic strength order. Now one question I'm giving you as the homework, you are going to tell me its order. HClO4, HClO3, HClO2 and HClO. Arrange all of these on the basis of strength of oxidizing agent. Tell me which oxidizing agent is stronger among all. Do tell me which oxidizing agent is stronger among all. Okay? And do let me know the answer of this question in the comment section afterwards when the session ends. When the session ends. Okay? One more question I'm giving you. Let's say you have got NH3. Let's say you have got H2S. Arrange them on the basis of their reducing agent capability. Which of the following, which reducing agent has got more strength? Strength of reducing agent. I told you strength of reducing agent, that is inversely proportional. Strength of reducing agent is inversely proportional to the oxidation state of central atom. So you can answer the question in this format. Nitrogen here is a -3, sulfur is in -2, right? And strength of reducing agent is inversely proportional to oxidation state of central atom. Lesser the oxidation state of central atom, more the strength of the reducing agent. Lesser the oxidation state of the central atom, more is going to be the strength of the reducing agent. So which reducing agent is stronger here? NH3 will be stronger than that of H2S when it comes to the reducing agent capability, right? Perfect. So guys, this is it for today, right? This question, I would want its answer in the chats, number one. I would want its answer in the comments. And I gave you one more question as the homework. Where did that go? Where did that go? Somewhere, some question I gave you as the homework, I think. Some question I gave you as the homework. Yes, this one. These are your two homework questions. I would want their answers in the comment section. And that's it. I think this much is enough. This session PDF, the handwritten notes I'll be sharing on this Telegram, which is t.me/WASSIMSIRCHEM. This is my Telegram channel on which I shall be sharing the handwritten PDF of today's session right after this particular session. Okay? And when this session ends, let me know in the comment section of this particular video, how did you like it? Okay? Do you want all the sessions to be detailed in this format? Do you want the sessions to be compact? Do let me know exactly how you liked it. Okay? Right? I'll be personally checking your all comments once the session ends. Okay? Do mention it in the comment section. Chalo, with this, I'll be taking a leave. Right? Take care. God bless you all and love you all. And at the same time, guys, today we have started the Phoenix Pro batch. All the NEET 2025 aspirants who would want to join into that batch, you guys are most welcome, right? The batch has started today. So still you have got the chance to enroll into that particular batch. You guys can join in. And the link is there in the description box of the video, wherein in that particular batch, we are completing the whole syllabus in 6 months, followed by 2 months of revision. On every alternate Sundays, we keep the tests, one-on-one mentorship sessions with me, with all the educators, with the single-digit, double-digit rankers, right? Okay. Perfect. So link is there in the description box. Do let me know in the comment section. I don't want anything in the chats. No chats. In the comments, I want your comments. I want to see your comments, right? I exactly want to see how do you feel after attending the first session. And one thing I would want the comments as well, it's going to be mentioned like this: day 1 completed. Day 1 completed. So today was our day 1. This is again something which I would want in the comment section. Day 1 completed. Chalo. Take care. God bless you all and love you all, guys. Bye-bye.